Projectiles launched at a horizontal don't go as far as projectiles launched at an angle. This is an observation you've probably seen or felt in any type of game. If you throw a baseball or basketball straight, it's not going to have as much distance as if you throw it up at an angle. Let's discuss the physics behind throwing a projectile or launching a projectile at an angle. Let's discuss some of the terminology related to projectiles launched at an angle. This is the general shape that an angled projectile will follow. This is parabolic. We saw a similar curve when we had horizontal projectiles. In fact, if you look at the second half of the motion to the right, it looks very similar to a horizontal projectile's trajectory. The angled projectile motion's trajectory includes the trip up and the trip down. The maximum height, the point where the object or projectile turns around as far as direction, it happens exactly halfway through the trip. This is halfway through time-wise and halfway through the horizontal distance of the trip. So if I divide the range by 2, I can know exactly when the projectile will hit its maximum height. If I divide the total time by 2, I'll be able to find exactly how far along it is when it hits its maximum height. The range takes the total flight. So if I'm trying to find the horizontal distance, I'm using the total time. Let's look at an example problem to highlight all the concepts behind an angled projectile. Calculate the maximum height and range of a projectile shot at 100 meters per second at 35 degrees. This highlights a very key difference between horizontal and angled projectiles. Horizontal projectiles are always projected horizontally, so straight forward, they move in a straight line. Angled projectiles now have angled forces applied on them. We know that angled forces create horizontal and vertical forces. We need to look in 2 dimensions. The same is true for velocities. So if we know the initial velocity of the projectile and angle, we can use trig to calculate the initial velocity both vertically and horizontally. Now you could set up a triangle and find the trig ratios and solve this for yourself, but these are some quick shortcuts. If I need to find the horizontal velocity, I take the angled velocity, so in this case 100 meters per second, times the cosine of the given angle, 35 degrees. If I want to find the vertical velocity, I'm going to take the given velocity times the sine of the given angle. This is a great shortcut that you can use in order to find those initial velocities. To highlight why this works, we're trying to find the maximum height and the range. So that's the vertical distance and the horizontal distance of a projectile shot at 100 meters per second at an angle of 35 degrees. So I'm given 100 meters per second. That is not forward, that is not up or down, that is at an angle. So that means that our velocity is the hypotenuse. In order to find the other legs, we need to look at trigonometry. The other legs are going to represent our vertical and horizontal initial velocities. If I want to find my vertical initial velocity, I'm going to take sine of the angle times the velocity. So 100 times sine of 35 gives me 57.4. To find the horizontal given or initial velocity, I'm going to do the same thing, but I'm going to use cosine. So it's 100 times cosine of 35 equals 81.9 meters per second. The vertical leg, so the red leg in this case, is our vertical initial velocity. That's how fast this projectile is going when it leaves the ground, or when it's projected out. Horizontally, it's moving at 81.9 meters per second. So the shortcut is vertical sine of the angle times the velocity. For horizontal, it's the velocity times cosine of the given angle. This is my given information. With horizontal projectiles, you're usually just given those velocities. With angled projectiles, you need to work for it first. So remember, the vertical leg is my vertical velocity. The horizontal leg is my initial horizontal velocity. This is just our given information. In order to solve for anything, we need to fill in the assumed information. Just like horizontal projectiles had assumed information, angled projectiles do as well, but they're slightly different. Because the vertical height or the vertical distance here occurs halfway through the projectile or halfway through the trajectory, we're only looking at the first half. We're looking at the trip up. If I throw a ball in the air, what happens to it on its flight up? It slows down. It slows at a rate of negative 9.8 meters per second. So remember, when the the direction and the motion are opposing, we have negative acceleration. So that's why it's negative 9.8. Horizontally, it's still moving at a constant velocity, so it has no acceleration, 0 meters per second. For kinematics, 3 is the magic number. I don't see 3 pieces of information anywhere on this problem, so I need to think logically. Initially, I have a velocity. With horizontal projectiles, we did not have a final velocity because the final motion was the object hitting the ground. In this case, the vertical motion is just looking at the trip up. It's looking at the first half of the trajectory. So that means it does have a final velocity. If I throw a baseball straight in the air, it slows down on the way up. It changes directions at the very top, where for one moment, one brief moment, it's going 0 meters per second. Then it returns and speeds up on its way down. This gives us enough information to find either the distance or the time vertically. When we're looking vertically, remember, we're looking at just the first half of the motion. We're looking at the trip it takes as it gets to its maximum height, which is also half of the total distance and half of the horizontal distance it's traveled. The second half of the trip gets it its full horizontal distance and its full time. So the horizontal time is twice as large as the vertical time. This is the total trip. We're looking at the first half and the total trip, the total trajectory. Let's find time first. Time is not equal in this case, but finding the vertical time will help us find the horizontal time. So look at the information that I'm given. I have 3 given pieces of information, 1 that I'm looking for, and X is left out. Remember to use only the vertical information. The horizontal information, we don't have enough, and I can't mix horizontal and vertical motions. So I find my formula that has X not included, solved for T. I'm going to plug in my given information. V, my final velocity, is 0. V sub 0, my initial velocity, is 57.4. And A, my acceleration, is negative 9.8. So I'm going to plug all that in. 0 minus 57.4. Notice there's a lot of negatives going on here. 0 minus 57.4 gives me negative 57.4. Negative 9.8 is still negative. Watch those negatives. So in this case, when I divide negative by negative, I should get a positive. This is a rational expression inside of our formula. So remember to simplify the top, simplify the bottom, and then divide. So I should get 5.86 seconds. In order to find the horizontal time, you have to remember that horizontal time is twice as big as vertical time, which means the opposite, vertical time, is half the time of the horizontal time. So to find vertical, you're going to divide the horizontal by 2. And in this case, to find the horizontal, you're going to multiply the vertical by 2. This is because that vertical point, that maximum height, occurs halfway through the trajectory. So I'm going to multiply 5.86 times 2 to get 11.72 seconds. Now I can find my vertical height or my horizontal height. Time is usually the missing key. It's usually the first variable you want to solve for because it gives you at least 3 given pieces of information in the vertical and horizontal column. So it'll allow us to do things like solve for X. The original problem asked me to find the maximum height and the horizontal range. The maximum height is the X, or the distance, vertically. Because we're looking at just half of the trip vertically, we're going to hit the maximum height exactly halfway through it. So I'm going to use just the vertical information. 1/2 still 1/2. The acceleration's negative 9.8. Time is 5.86. Initial velocity is 57.4. and time is still 5.86. Now it's just a matter of doing order of operations. So I'm going to take care of my exponents first. I'm going to multiply, keep taking care of that multiplication until I finally add everything together. Showing your work this way, doing one operation at a time, following the order of operations, really, really helps. This way, if you make a mistake, if you get an answer that's not reasonable, something that's negative, something that seems too big, too small, seems illogical, you can go back and double check where you made a mistake. If you just typed everything straight in your calculator, 9 times out of 10, you're going to assume that you're right. You'll ignore everything because you put too much trust in a calculator. Show your work, use your calculator to do your work, but show each step so you know where your mistakes happened. So we get a vertical distance, a maximum height of 168.09 meters. Let's find the horizontal distance. This is the total range. So we're going to end up using the same exact formula. So I left out, to pick the last formula, I actually left out final velocity. This formula is a safe bet. This is the same formula we used a lot when we were calculating horizontal projectiles. So I'm going to plug in just the horizontal information. Make sure you do not mix and match. So I'm going to throw in 0. Time is twice that of the vertical. Initial velocity is 81.9. And the time is, again, twice that of vertical. Because I'm multiplying by 0 on the left side of this side of the equation, that whole side equals 0. 1/2 times 0 is 0. 11.72 squared times 0 is 0. So we can just cancel that out. We end up with just the initial velocity times the time. So I multiply those two together to get 959.89 meters. Which again makes sense. We want to have a longer distance. This object is going to go further than it did higher. This is a reasonable answer. Couple big ideas to take away from this. Take the initial velocity and calculate the horizontal and vertical velocities using our trigonometry. You can either set up the trigonometry like a triangle or use the shortcut. Some of our information, some of our assumed information includes adding the final velocity of 0 meters per second to the vertical table. This is how fast it's going exactly halfway through the flight when it changes directions vertically. Remember, on the way up, it's going up, slowing down, it changes directions, and then it goes down, speeding up. We're going to use an acceleration of negative 9.8 meters per second squared. This makes sense because on the way up, so just the first half of that trajectory, it's slowing down on the way up before it changes directions and then speeds up on the way down. Use the kinematic equations to calculate the max height using only vertical info. Max height is a vertical distance. The total range is a horizontal distance. So if you want to find the total time and the horizontal range, use horizontal information. To find half the time and the vertical height, use the vertical information. Oftentimes, you'll end up using the same equation in both cases, but you'll be using different information when you plug things in.